Well, we'll look at an application, really an engineering application of the magnetic force, and that's this application called the velocity selector. If you had been the first to figure this out and had patented it, you could have gotten a fair piece of change probably by the time things were over. A selector is really a fairly simple device. We often have a bunch of identical particles that are created in a beam, but they have different velocities coming in here. And it would be nice in certain applications, you'd like to create a beam of electrons, say, or whatever the particle is, that has exactly the same kinetic energy, has the same energy, total energy, as it gets fired through here. And so an idea that came to people was that you could use crossed electric and magnetic fields to select out a particular velocity from maybe a beam of particles that have a spread of velocities in them, all going in this from left to right, but having different speeds. And the way you do is you apply a magnetic field. Here I've got the magnetic field coming out of the page at us. I'm assuming we've got a positively charged particle that moves through here. At some point it gets into the field, and I'm assuming we want the one that's got the velocity v here selected. You can look at it, but v cross b for a positive particle, the magnetic force is going to be downward, and and if that were the only force present, then it would curve downward. This positive particle would be deflected downward and probably eventually hit this plate. However, what I'm going to do is I'm going to apply a positive and negative potential difference across here. That creates an electric field E naught that's upward. Remember, electric fields, I've got some field lines drawn here and here. Always go from the positive, the high potential side, to the low, or the positively charged plate. And I choose that direction because I know that for a positive charge, the force of the electric field on it is Q V cross B, or is Q times V, not cross, but Q times V. And so I've got an electric force on the particle up in this direction caused by the electric field. I've got magnetic force by the magnetic field. Now, if it's going slow, very slow, the magnetic force, this is weaker because it's going to depend on the velocity, and so the electric field is just a constant, and so that's going to deflect it upward and hits this plate. So if it's going too slow, it's going to deflect upward because the electric force will be stronger than the magnetic force for slow velocity. On the other hand, if I fire in a very fast particle through here, well, the electric force stays the same, so this stayed the same, but the magnetic force, it depends on the speed, so it will get stronger and that'll pull it down to this plate. So some are too strong, some are too weak, depending on the velocity. But there's one velocity that's just right, like Goldilocks and the Three Bears, just right, the velocity coming through. And for that velocity, we have exactly the upward force, the QE, is exactly balanced by the magnetic force. And if that's the case, there's no net force on that chosen velocity, and it goes right straight through. And so all the other velocity particles that's in this beam, they hit one plate or the other. The chosen velocity goes straight through, and so what emerges over here is a beam of particles, all of which have the same kinetic energy and the same speed. Well, if you look at that, what we did in terms of a vector, we have the total force on this charge is the electric force plus the magnetic force. Electric force was Q E naught. The magnetic force was Q V cross B naught. If I want to have just the right velocity so that this vanishes, then the total force is 0. And then another kind of a miracle occurred. I didn't really say anything about the charge in this formula, but because it divides out. And so it doesn't really matter whether this is a positive charge like I've drawn or a negatively charged. As far as this net force being, it vanishes here because I divide out the charge. And I see that to select out a velocity v, I have to have e vector, e naught, equal to minus, take this over to the other side, minus b vector across b. And they're both uniform, I'll assume, so I probably should have put a b naught here as well. Oh, I did there later, okay. And now then I just take the magnitude of both sides of this. So the magnitude of e naught is going to be the magnitude of this term. The magnitude of e naught is just e naught. The magnitude of v cross b, well, the minus sign, that goes out in the magnitude. It's going to be the magnitude of v, that's the speed. Magnitude of b naught, that's the strength of b. And then the angle between them, well, if you look at it, the way it's drawn, the magnetic field is out of the page, and v is in the plane of the paper, so out of the paper and plane of the paper. And as a result, the magnitude VB sine of the angle between them, but the angle's 90. And so one can solve for the velocity that you select for. Usually you have the magnetic field fixed, and you change the E naught by simply changing the potential difference across these two plates. That increases the strength. And that gets you different velocities. But in any event, the speed that is selected in the velocity selector is E naught over V naught. And that's the speed of particles that it allows to pass straight through. All the others don't make it, and we've got a nice pure beam of particles all having exactly the same speed, and therefore all having exactly the same kinetic energy if they all have identical masses, which I'm assuming here as well.